I'm David Thompson, and this is the next lecture in the series on dimensionality reduction. It's part of the JPL Caltech Virtual Summer School in Big Data Analytics. This is a fun lecture. This is where we actually start to get into real dimensionality reduction proper. So we've kind of danced around it a bit in previous lectures. I've described the curse of dimensionality, why high-dimensional data sets can be problematic for pattern recognition. And then I described some feature selection strategies where you can reduce dimensionality by selecting subsets of those attributes. Here we're going to get into the purview of what most folks think of when they think of dimensionality reduction, which is actually coming up with interesting projections of the data that utilize all of the attributes but represent the data in some lower dimensional space that we can more easily visualize, and that it's easier for our pattern recognition algorithms to use. So we're going to be discussing linear methods here. All right, the objectives of this talk, you should become familiar with dimensionality reduction and its relationship with feature selection, and understand linear dimensionality reduction, here principal component analysis, and its relation to singular value decomposition. And then finally, we'll be talking about eigenfaces too. All right, so dimensionality reduction relies on the intuition that even though these high-dimensional spaces are very difficult to deal with, it's almost never the case that our data actually fills the high-dimensional space completely. Real processes aren't like that. It's very rare that you find a process that actually has thousands of intrinsic parameters along which it varies, right? More commonly, the process that generates our data is some lower dimensional structure that's embedded in this high-dimensional space, right? So this is commonly represented as some sort of a manifold or a subspace that lives in our higher dimensional attribute space. And the point of dimensionality reduction is to reveal or uncover that manifold or that subspace. Here we see an example. So you may recall from earlier lectures where I talked about image analysis as one area where we have to deal commonly with high dimensional data, right? If you have, say, a thumbnail image that's 20 pixels on a side, that's 20 times 20, 400 different attributes of potential variation, right? It's a very high-dimensional space. But in practice, many of these data sets have a much smaller intrinsic dimensionality. That is, they lie in a low-dimensional manifold of that 400-dimensional space. Here's an example from a famous dimensionality reduction paper showing images of hands. So we've got probably a couple hundred data points here. These are the blue points that I've plotted in just 2 dimensions. And we've projected these data points down onto this 2-dimensional plane in such a way that neighboring points are similar to each other and distant points are dissimilar. And you can see that there are actually only 2 dimensions of intrinsic variation in these hand images, right? If you know the coordinates in this space, right, in this 2D space, you can specify exactly what the hand image is going to look like. The 2 dimensions that we've labeled are the wrist rotation and the extension of the fingers, right? And with those 2 parameters, you can adequately describe any one of these images. So this is a case where there's some lower dimensional manifold that we've uncovered. Here it's a nonlinear manifold, right? We'll get to this in later talks, but you can imagine that there are linear subspaces that would describe this data set more efficiently as well. And it's almost always the case that you can come up with some lower dimensional projection that preserves all of the information in your data set while reducing redundant dimensions. So let's start off with some formal definitions before we go any further. Again, we'll be looking at data points which are column vectors. So here, a column vector x has n attributes. So we're listing these attributes from 1 to n as a column. And you can stack them together in a matrix row-wise. So we have an n by d matrix where d is the total number of data points in the data set that we're trying to project. And what we're aiming to do with dimensionality reduction is project these onto new data points, which I'll here represent as y, that have some lower dimensional representation. So here we have just m attributes where m is considerably less than n, right? So this is some lower dimensional subspace. And dimensionality reduction is just this mapping. Okay, so for linear dimensionality reduction, which is probably the most common form
of this algorithm. We'll define the mapping from x to y to be linear. That is, you can think of it as just pre-multiplication, a new basis for representing the data that has a smaller dimensionality than our original basis, right? So we can represent that as an m by n projection matrix, and if we pre-multiply it with the x matrix, then this gives us the desired projected data matrix y. So we're finding a subspace that best represents the data. And the most common approach to doing this, to finding the subspace, is called principal component analysis, or PCA. Now, PCA is quite common, so you may have come across it in your own disciplines, right? It goes by a variety of different names. In the earth sciences, it could be called the empirical error function or the empirical orthogonal function. In a lot of times in remote sensing, it's known as the minimum noise fraction transform. It may have other names in other disciplines. So it's highly likely that you've encountered this before, but it's good to review because it's just so darn useful. And even for a data set that isn't truly on a linear manifold, often sort of a coarse PCA reduction of the initial dimensions onto some smaller linear subspace of the data will still yield benefits, even if you then go on to subsequently apply some other sort of analysis, some other nonlinear mapping or pattern recognition after that. Principal component analysis is almost always a good thing to do. So it's a really fundamental tool in the toolbox. The goal of principal component analysis, or how it identifies this basis, is to find the orthogonal directions that maximize the variance of the data set. So here's an example of a data set in 2 dimensions. You can imagine projecting this onto a one-dimensional subspace, right? So we want to project this onto a line. We want to draw a line somewhere in this data cloud that allows us to optimally reconstruct the data set, or equivalently maximize the variance along that projection. So how would we do it? Which line would you choose if you were to analyze this data set and you had to come up with a single linear direction onto which all of your data would be projected? Well, obviously you'd want to follow the direction of variation, that is this main axis. So the first principal component is indeed aligned with the main axis of variation. So if you project all of your data points onto that red line, or that red direction, then that will maximize the variance of the resulting projection. And equivalently, if you wanted to reconstruct a data point from its position along that line, you'd get pretty close to the original point using that direction of variation. So one thing to notice about this data set that I'll get back to in a couple slides is that it's centered at 0. So this is an important feature of the principal component analysis. The data cloud really has to be centered. Now, it's easy to center any data cloud, right, before applying PCA. Simply subtract off the mean, right? But that's an important step, and one that will be important as we start looking at nonlinear analogs of PCA. Okay, so there's our first principal component. It's pretty obvious. Our second principal component to this data set would have to be orthogonal to that one, right? Because, again, PCA dimensions it's an orthogonal basis. It's an orthonormal basis. So the second principal component would come out perpendicular to the first. So note also that these vectors have unit length. Our goal here is to provide a true basis that is a rotation of the data in which everything is orthogonalized and sort of independent. Okay, so this will require a new construction, which is the covariance matrix that I want to introduce here if you're not familiar with it already. So covariance matrix is simply the matrix of all the covariances between all of the different attributes in your data. So this is the formal definition, where you have the covariance matrix that we're representing here as sigma sub x. The sigma sub x for attributes I and j is the expectation of the attribute x minus its mean times the attribute j minus its mean. I'm sorry, the attribute y minus its mean times the attribute j minus its mean. And you can put all these together element-wise into an m by m matrix, where m is the total number of attributes in your data set. You can estimate that using what we call the sample covariance matrix, which is represented by this expression here in the center of the slide. Take essentially the data set and its cross product and divide by the total number of data points minus 1. Okay, so the properties of this covariance matrix. Well, the diagonal terms have the variance
of the different attributes of X. And the off-diagonal terms, like I said, represent the covariances of X. The matrix itself has some unique and important properties. In particular, well, it's square, obviously, and it's symmetric, but it's also a special class of matrices known as positive semi-definite. And every positive semi-definite matrix is a valid covariance matrix, and vice versa. And it will be important to maintain this property of positive semi-definiteness in the future, particularly as we look at the nonlinear analogs. Okay, so how would this work in practice? How do we maximize the variance of a projection? How do we identify the appropriate projection to use? Well, here on the left side, you can see we can rewrite the variance of our projection as the expectation of the projection. Here I've noted the projection itself, the projection vector, as a vector v, which I'm multiplying. I'm basically taking the dot product of that with x, and that gives me the projected location. So the projected location of a data point minus its expectation, that quantity squared, or the expectation of that quantity squared, is the formal definition of the variance. And you can, through some algebra, expand this and get the expression in the center, which is the expression v times the covariance matrix times v, and then it's basically it's known that for a zero mean covariance matrix, the unit vector that minimizes this quantity is the top eigenvector of the covariance matrix. So it's simply the solution to the eigensystem that starts with the sample covariance matrix and then gives you the eigenvectors of that sample covariance matrix, which is the expression in the lower right. So it's basically a straightforward eigensystem, and there exist lots of numerical packages that will solve this efficiently. MATLAB has a bunch of them, but the eigs function is particularly useful here. And another useful property of this whole procedure is that you only need to calculate as many eigenvectors and eigenvalues as you want to have components, right? So if you are projecting the data onto the top 6 principal components, then you only need to calculate the top 6 eigenvectors, and that's enough. So there are efficient iterative strategies for doing this, and it makes it a pretty straightforward calculation. So in summary, what's the PCA recipe? You convert the data to have zero mean, that is, you subtract off the mean of the data set, and then you form the sample covariance matrix, or you form your projection matrix, which in this case is A, using the top n eigenvectors of the sample covariance matrix. Or equivalently, and I'll get into this in greater length later, there's a similar formulation that uses the singular value decomposition of the matrix X. Okay, so this gives you a matrix A, which is your orthonormal basis, and then in order to project the data to a lower dimensional space, you subtract off the mean of a new data point, and then pre-multiply that orthonormal basis X, which gives you the projected data point Y. To reconstruct the original data point from its projection, you multiply by the transpose of your projection matrix and add back the mean, and that gives you a reconstruction, which I've here noted X hat. All right, so it's a fairly straightforward procedure, and it's useful for a wide range of different pattern recognition problems. I'm going to talk now about one canonical example of principal components analysis, which is called eigenfaces. And they've been doing this for many decades. Here's an example from Moghadam et al., where they apply this to a fairly well-known data set called the Ferret Frontal View Image Database. Here we're projecting these data points, where each data point is a face, onto the set of basis vectors which best represent variance among different faces. So you can use this for face recognition, for detection of faces and new images. Eigenfaces are sort of universally useful for all sorts of face recognition problems. Here are the first top 8 principal components of the face data set. And it's interesting that these have their own sort of distinct interpretations. So starting with the first principal component there in the upper left, you can see that there's a lot, that bright patch on the forehead suggests that maybe this principal component is concerned mostly with, say, features of the hairline or of illumination on the forehead. Perhaps the second principal component right next to it, moving right, It looks like there's some shading there, so perhaps the second axis of variation has to do with, say, illumination differences from left to right. You can see in the third principal component that there's definitely something to do with the hairline there and the forehead, and so on and so forth. You can see different features pop out in the principal components, such as structure in the face and cheeks, the position of the eyes and eye sockets. There's even an obvious expression change in the principal components, and all of these are sort of distinct axes along which the data can vary. So the principal components, interestingly enough, are themselves interpretable as directions of variance in the data set. Right, so they can be informative in their own right. You can also interpret the eigenvalues. So the eigenvalues associated with that eigensystem that I showed you before tell you a bit about how many principal components you need to use. And in particular, here's the chart of all n eigenvalues. There's a dramatic fall-off initially after the first, few eigenvalues of the system. Right? And what that means is that the intrinsic dimensionality of this eigenfaces data set is actually much lower than the full number of attributes, n, right? That we can capture the majority of the variance by just using a much smaller set m, and in fact that's typically what people do. They could use the top, say, 10 or 20 dimensions, which would be much better than using all like hundreds or thousands of dimensions in the original face data set. Right, so the eigenvalue plot here gives you some indication of just by where that fall off starts to asymptote exactly how many eigenvectors you need to include in your orthonormal basis to adequately capture the variance of the data. All right, I want to close with a few notes on how to implement this efficiently for very large dimensions or very large numbers of data points. Obviously, even these calculations can be onerous for a very large D or very large N. Things like computing the sample covariance matrix can be challenging for the large numbers of data points, and computing its inverse can be challenging for very large dimensionality. There are efficient ways to handle this. One of the most common ways is to use singular value decomposition. So it turns out that solving that eigensystem that I showed you before is equivalent to performing singular value decomposition on the data matrix. And you can simply use the left singular vectors, or the left vectors u here, which are column vectors of that singular value decomposition matrix, together with the top singular values in the diagonal matrix D instead of your eigenvalues, and that amounts to the same thing, actually. So and because there are efficient singular value decompositions and incremental singular value decompositions, you can use these to improve the computational performance on very large data sets. Another approach is to just calculate one principal component at a time. I alluded before to iterative solutions to the eigensystem. Roeis et al. in NIPS provide a method for calculating one principal component at a time. Another method would be to use an online learning strategy where you train principal components analysis on a subset of the data and then iteratively update that or improve it sequentially in sort of an online fashion. So you could use a sequential estimation approach. And there's other literature about how to do that. So it's not so important that you know offhand how to do this, but simply that you know that these methods exist in the literature, and that if you get stuck with a problem that's too large for naive principal component analysis, that there are other alternatives for computing these solutions more efficiently. All right, so to summarize, principal component analysis is it's a terribly useful tool to have in your toolbox. It's a reliable standard method for dimensionality reduction and visualization. The objective is to find an orthonormal basis that maximizes the variance of the projected data in the resulting new feature space. And the basis vectors and eigenvalues can also be interpreted to provide insight about the data set, in particular what the principal axes of variation are, and also what the intrinsic dimensionality of your data set is, which is what the eigenvalue analysis provides.